Every culture, every civilization has asked the same question. Where did it all begin? For centuries, human beings looked up at the stars and wondered whether the universe had always existed or whether it had a starting point. Philosophers debated eternity. Religious traditions spoke of creation, and scientists once assumed the cosmos was infinite and unchanging. But in the 20th century, an idea emerged that shattered those assumptions. The universe had a beginning, a moment of birth, we now call the Big Bang. The term Big Bang is almost misleading. Conjures up images of an explosion in space like fireworks against a night sky. But the reality is far stranger. The Big Bang wasn't an explosion in space. It was an explosion of space itself. The universe expanded from an unimaginably hot, dense state where all matter, energy, and even the dimensions of space and time were compressed into a singular beginning. This is not just a story of astronomy. The Big Bang is the foundation of modern cosmology. The attempt to understand not only what the universe is made of, but why it looks the way it does today. It explains the birth of matter and light, the origins of galaxies and stars, and even the chemical ingredients that make up our own bodies. Yet for all its triumphs, the Big Bang theory raises as many questions as it answers. What existed before time? What triggered the expansion? How did tiny fluctuations in the newborn universe grow into the vast cosmic web we see today? Before Einstein, most scientists assumed the universe was static. Space and time were absolute, unchanging, and infinite. Stars had always been there, and would always be there. Then came Einstein's theories of special and general relativity, which showed that time intertwined with space was relative and could change depending on your frame of reference. Gravity wasn't a force, but the effect of curved space-time caused by mass. These ideas turned the universe from a fixed stage into a dynamic, ever-changing entity. If the universe was expanding, that meant it had to have a beginning. And if it began, then it had to end. Somewhere between these two poles of thought was the work of Georges Lemaître, a Belgian priest and astronomer who in 1927 became the first person to propose a primeval atom. Lemaître imagined the universe compressed into a hot, dense state, then expanded outward like a balloon being blown up. His idea gained traction after Edwin Hubble discovered that galaxies were indeed moving away from us. And the farther away a galaxy was, the faster it receded. This observation, known as Hubble's law, provided the final piece of the puzzle, cementing the idea of an expanding universe. But there is still no accepted theory of the Big Bang. That breakthrough came in the late 1940s when American cosmologist George Gamow and his student Ralph Alford combined the concepts of an expanding universe with nuclear physics. Their model predicted that the universe was born in an intense hot plasma state, a sea of subatomic particles. As the universe expanded, these particles combined to form the first elements, hydrogen and helium. Most important, the model predicted the cosmic microwave background, a faint glow of radiation that permeated all of space. The Big Bang model without the background radiation was like a melody with no harmony. But in 1964, Arno Penzias and Robert Wilson of Bell Telephone Laboratories accidentally detected this radiation. Confirming the Big Bang model and launching the scientific quest to map the universe. Today, the cosmic microwave background is the most detailed map we have of the early universe, capturing light just 400,000 years after the Big Bang. What it reveals is a universe already in motion, rippled with tiny temperature variations. These ripples, though small on the scale of the entire universe, were the seeds of cosmic structure, the invisible scaffolding that would eventually collapse into the galaxies, stars and planets we see today. But why were there these ripples in the first place? Enter Alan Guth, a physicist who in 1980 proposed a solution known as inflation. Guth's idea was that the universe underwent a period of exponential expansion driven by a mysterious force called dark energy. Inflation lasted for a fraction of a second, yet it amplified quantum fluctuations across the entire universe, giving rise to the large-scale structures of galaxies and galaxy clusters. Today, scientists are testing Guth's idea by looking for telltale signs of inflation in the cosmic microwave background. If they find it, they may also find evidence of other universes, creating a multiverse where our universe is just one bubble in a vast cosmic ocean. And finally, we come to the mystery of dark matter. Scientists believe that normal matter, the stuff that makes up stars and planets and people, accounts for less than 5% of the universe. The rest is made up of dark matter and dark energy, to phenomena we cannot see directly but whose presence we can detect through their gravitational effects. Dark matter is the scaffolding of the cosmos. As gravity holds galaxies together, dark energy is the driving force behind the accelerating expansion of the universe. Together, these dark components make up 95% of the cosmos, yet we know next to nothing about them. Here we reach the frontier of knowledge. We have mapped the birth of the universe, traced the path of its evolution, and charted its trajectory into the future. We have seen how the Big Bang explains the chemical elements that make up our bodies, and how the same forces forged the elements inside stars that one day became Earth. Looking forward, we face a universe that will either expand forever or collapse in on itself, leaving only the black hole remnants of dead stars. Either way, we find ourselves at the center of a grand cosmic drama that began with the Big Bang and continues to this day. Our story is the story of the universe, and the fate of the cosmos is our fate. This is the series Cosmos, a space-time odyssey. In the year 1000, the most powerful telescope in the world could resolve objects no larger than Jupiter at the edge of the solar system. Today, from Earth and space, we can see back to within a few 100 million years of the Big Bang. We've traveled back in time almost as far as we can. So, let's rewind the film and find out what happened just after the birth of the universe. We begin with the obvious question: what exactly is the Big Bang? Well, it's not an explosion in the usual sense. There was no outside force pushing something outward. Rather, the term refers to the rapid expansion of space itself. Think of it like a growing balloon. As the rubber stretches, each marked on it moves apart from its neighbors. That is what is meant by an expanding universe. But where did this expansion start? To answer that, we need to go to the earliest moments when gravity was not the force we know, but an infinitesimal quantum of energy rippling through a boundless void. Our best guess comes from the most successful theory we have ever devised to describe reality: Einstein's general theory of relativity. It tells us that massive objects warp the fabric of space-time around them. The more massive the object, the greater the warp. When we move around, we follow the curves dictated by these warps. That is what we call gravity. But the situation was completely different in the first fractions of a second after the Big Bang. There were no large objects around to carve out space-time. Space-time was flat and featureless. We're talking about an era known as Planck time, named after the physicist Max Planck, who calculated that the earliest period of time we could even theoretically conceive of was about 10 to the minus 43 seconds. The defining property of this era was that quantum effects were dominant. The universe, if we can call it that, was in a perpetual state of flux. Tiny bits of energy were jiggling around, warping and unwarping space-time. But then, something remarkable occurred. Those jiggles started to fade. Space-time began to smooth out. As it did, the tiny ripples of energy condensed into particles of light and matter. In a fraction of a second, the universe went from a featureless plane to a sea of particles. At this point, we can stop calling it the Big Bang, because the concept of an instant doesn't apply at such short distances. The universe was too small to have any meaning. We don't know exactly what happened next, but we have some clues. Let's start with what we do know. First, the universe was extremely hot and dense. Within a second, the temperature reached 10 trillion degrees, 1 trillion times the temperature at the center of the sun. Second, it was filled with elementary particles, quarks, electrons, muons, neutrinos, and photons. Third, all of these particles were moving so fast they didn't have time to combine into anything more complex. In short, there were no atoms yet. Under these conditions, protons and neutrons could not form until the universe cooled sufficiently for them to bind together. Fourth, the universe was transparent. All of those photons were zipping around freely. That changed as the universe expanded and cooled. Photons slowed down and combined with protons and neutrons to form hydrogen and helium atoms. Once the universe had cooled below 3000 kelvins, the free electrons that had been flying around combined with those nuclei. This soup of newly formed atoms was opaque, and the universe became what we call the surface of last scattering. No photons could get through. Finally, fifth, the universe was remarkably homogeneous, very similar throughout. To see why this is significant, imagine a box of popcorn. Popcorn kernels placed close together tend to explode outward. If you increase the density, you get more vigorous explosions. If instead you spread the kernels far apart, the explosions are less energetic. It turns out that the entire universe behaves like popcorn. The higher the density, the faster the expansion after the Big Bang. In other words, the more matter there is, the faster the expansion. This has profound implications because it means that tiny variations in density, in the distribution of matter, would grow into large-scale features today. But at this stage, the universe was so smooth that even a quantum fluctuation would have been noticeable. Fluctuations would have smoothed themselves out. Homogeneity tells us that the early universe must have been extremely orderly, but order is rare. It requires constant maintenance. Thus, the fifth feature gives us our first hint of an important process that shaped the universe: inflation. Most physicists today believe that in the first tiny fraction of a second, the universe expanded faster than the speed of light, known as exponential inflation. This rapid growth could have generated the large-scale structure of the universe, including galaxy clusters and superclusters. Inflation also would explain why the universe looks so similar in all directions. Any region we see today was once part of the overall smoothness. During inflation, the universe grew by a factor of more than 1 followed by 26 zeros. To put it another way, if you took a piece of bread the size of the observable universe and cut it into pieces the size of galaxies, there would be more pieces than the number of all humans that have ever lived. And still, the universe would look much the same. In short, the extreme conditions of the early universe drove home a fundamental lesson. Complexity tends to increase. Orderly states are unstable and break down into chaos. So far, we've looked at the early universe from a bird's-eye view, but now let's focus on a particular patch of space about the size of a grapefruit. This may seem arbitrary, but it's really the best choice. If you chose a patch of a different size, say the size of a star, the same processes would have been happening within it. Inside our grapefruit-sized patch, things were changing rapidly. Within seconds, the particles that made up the primordial soup began to come together. Quarks joined to make protons and neutrons. Next came atomic nuclei, and then the first simple atoms, mostly hydrogen, but some helium and lithium. After a few minutes, it was as if the primordial soup had suddenly thickened into plasma. We now know that this plasma contained the seeds of everything that would eventually form stars and galaxies, giant clouds of hydrogen and helium. The reason they were still clouds rather than discrete objects is that there was nothing to cause them to collapse. But this too would change, because as the universe continued to expand and cool, gravity began to pull those clouds into denser and denser knots. In the process, the knots heated up. Eventually, the core of one knot became hot enough to trigger nuclear fusion. One hydrogen atom smashed into another, forcing them to combine and release energy, and so the first stars ignited. These stars shone brightly and produced the heavier elements that enriched the universe. After millions of years of this activity, the universe had changed dramatically. Gone was the featureless void, and in its place was a vast array of luminous objects held together by unseen threads of gravity. To understand how those threads came about, let's return to the question of homogeneity. We noted that the early universe was very similar throughout, but that cannot have been entirely true. Otherwise, we could not be here, if you think about it. The fact that we can be here means that there must have been a slight variation somewhere in the early universe. Just how small a variation would have been enough to lead to everything we see around us is unknown. It would have been measured in parts in 100,000. But the crucial point is that such tiny variations could have gone unnoticed at the time. Since we don't know what exactly triggered the emergence of galaxies and galaxy clusters, we refer to this stage of development as the Dark Ages. It lasted from the formation of the first luminous objects to the first stars lighting up the night sky. We can only glimpse it by peering deep into space and seeing the faint red-shifted glow of the most distant galaxies. But even though we can't see what was going on during the Dark Ages, we know that the period ended when the first stars emerged, releasing ultraviolet radiation. This radiation ionized the surrounding hydrogen gas, gradually erasing the darkness and revealing the large-scale structure of the universe. Today, we see the results of this process all around us. Most of the matter in the universe is invisible, comprising a thin, tenuous fog that permeates galaxy clusters and extends throughout the vast emptiness between them. This is hydrogen and helium in their ionized state. In other words, the light from the first stars stripped them of their electrons. Because these gases are so diffuse, each atom occupies a huge volume of space. This intergalactic medium, as it is called, plays a vital role in galaxy formation. As gas falls into a galaxy, it forms new stars, replenishing the supply that is constantly being depleted by stellar winds and supernova. In effect, this recycling of material maintains the overall level of matter within galaxies, while triggering new bursts of star formation. And there we have it, the cosmic fingerprint of the Big Bang. Stretched and distorted by the expansion of the universe, imprinted on the oldest light we can detect. It points back to the moment when the cosmos erupted into being. This is the story of the birth of the universe. It is an epic tale that carries with it a simple message. From the tiniest quantum fluctuations to the largest galaxy clusters, everything in the universe is connected. The future hinges on the past, and the only way to understand the one is to explore the other. So keep looking up, keep asking questions, and above all, keep exploring. The universe is full of wonders, and we are just beginning to uncover them. The birth of the universe is a subject shrouded in mystery, a cosmic tale whispered to us by the faintest glow of ancient light, and echoed in the structure of the modern cosmos. 4,000 years ago, the idea of a universe that began with a single explosion was nothing more than fantasy. But today, the Big Bang Theory stands as the prevailing model for the origin of the universe. And yet, despite centuries of scientific progress, the truth of the universe's birth remains tantalizingly out of reach. When we say the universe began with the Big Bang, it was tempting to imagine everything happening in an instant. A single explosion followed by stars and galaxies bursting forth. But the reality is much more gradual and far stranger. The early universe was not filled with stars or planets or even atoms. It was a searing ocean of energy and fundamental particles evolving step by step through a series of cosmic milestones. To understand how the familiar universe arose, we need to trace this sequence of events across the first few 100,000 and then billion years. The first second, a universe of particles. In the very first fraction of a second, the universe was unimaginably hot and dense. Temperatures reached more than 1 trillion degrees, conditions so extreme that the basic forces of nature themselves behaved differently. Physicists believe that during these earliest instants, the 4 fundamental forces, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, may have been unified into a single force. As the universe expanded and cooled, these forces separated, a process called symmetry breaking. Almost immediately, matter and antimatter were created in nearly equal amounts. For every particle of matter, there was a mirror image particle of antimatter. When these two met, they annihilated, leaving behind pure energy. Yet somehow, a tiny imbalance occurred. About 1 extra particle of matter for every billion pairs. That tiny excess is why anything exists at all. Without it, matter and antimatter would have completely canceled each other out, leaving a universe filled only with radiation. This is still one of the great mysteries of physics. Why was there more matter than antimatter? Experiments in particle accelerators like the Large Hadron Collider try to probe this question, but the answer remains elusive. Whatever the cause, this imbalance set the stage for a universe filled with matter. The first minutes. Nucleosynthesis. After the first few seconds, the universe had cooled enough for protons and neutrons, the building blocks of atomic nuclei, to form. Over the next 3 minutes, these particles collided in a process known as Big Bang nucleosynthesis. In this brief cosmic window, the first elements were forged, primarily hydrogen and helium, with trace amounts of lithium. The amounts are strikingly precise. About 75% of ordinary matter became hydrogen, 25% helium, and just a tiny fraction lithium. Heavier elements like carbon, oxygen, and iron did not yet exist. They would only be created later, in the cores of stars and in the fiery deaths of supernova. This early recipe was confirmed billions of years later. When astronomers measured the chemical abundances of ancient stars and found them to match predictions from Big Bang theory with astonishing accuracy. The first 380,000 years, a universe of light and shadow. At this stage, the universe was still opaque. The hot plasma of electrons and nuclei scattered light constantly, much like sunlight scatters inside a dense fog. Photons, particles of light, could not travel freely, so the universe glowed, but nothing could shine through. That changed about 380,000 years after the Big Bang. By then, the universe had cooled enough for electrons to combine with nuclei, forming the first neutral atoms. This event is called recombination. With electrons locked into atoms, photons were no longer scattered constantly. For the first time, light could travel freely through space. That ancient light is still with us today. Over billions of years, the expansion of the universe has stretched its wavelength from blazing radiation into the microwave part of the spectrum. When we tune our instruments to those frequencies, we see a faint glow that fills the entire sky. The cosmic microwave background, CMB. It is a perfect snapshot of the universe at 380,000 years old. A baby picture of creation itself. The CMB is astonishingly uniform, but not perfectly so. Tiny temperature variations, 1 part in 100,000, are scattered across it. These small variations represent slightly denser regions of matter that would, under the pull of gravity, grow into galaxies, stars, and eventually planets and people. In these faint ripples of ancient light lies the blueprint of all cosmic structure. The Dark Ages. Before the first stars. After recombination, the universe entered a long, dark period. Neutral hydrogen-filled space, but without stars or galaxies, there was no source of light. For hundreds of millions of years, the cosmos was dark and cold. Save for the fading afterglow of the CMB, this era is sometimes called the Cosmic Dark Ages, but it was not uneventful. Gravity was at work, slowly pulling matter together. Over time, small density fluctuations. The seeds imprinted in the CMB grew denser, clumping into clouds of hydrogen and helium. These would become the cradles of the first stars. Cosmic dawn. The first stars ignite. About 100 to 200 million years after the Big Bang, something extraordinary happened. The first stars were born. These so-called population 3 stars were unlike anything we see today. It's made almost entirely of hydrogen and helium, with none of the heavier elements that later stars contain. They were likely far more massive, perhaps hundreds of times the mass of the Sun. Because of their size, they burned hot and lived short, exploding in violent supernova after only a few million years. These explosions were critical. They created and dispersed the first heavier elements, carbon, oxygen, nitrogen, and iron, seeding the universe with the raw ingredients for planets, life, and future generations of stars. The deaths of the first stars were the first chapter in the cosmic story of chemical evolution. The reionization era, lighting up the universe. The light from the first stars began to transform the cosmos. Their intense radiation ionized the surrounding hydrogen gas, ripping electrons away from atoms. Over hundreds of millions of years, this process spread across the universe, ending the Dark Ages and creating a transparent cosmos once again. This era, called reionization, marks the moment when the universe became filled with light. Reionization is still being studied. Telescopes like the James Webb Space Telescope are peering deeper into space, and therefore further back in time to catch glimpses of the first galaxies forming and to understand how quickly the universe lit up. The birth of galaxies and cosmic structures. From this point onward, the universe began to resemble the one we see today. Stars gathered into galaxies, galaxies clustered into groups, and those groups stretched into vast filaments, forming what we now call the cosmic web. This web-like structure, a vast skeleton of dark matter and galaxies, stretching across billions of light years, is one of the most remarkable patterns in nature. The seeds of this structure can be traced directly back to the tiny fluctuations in the CMB. In this sense, the galaxies, stars, and planets we know today are nothing more than the amplified echoes of microscopic ripples in the infant universe. However, this narrative is far from complete. The story of the universe's birth raises more questions than it answers. We marvel at the precision with which the elements were forged in the furnaces of the early universe, yet we still struggle to understand the delicate balance of forces that led to the formation of complex structures like galaxies and stars. The universe seems to possess an inherent tendency to evolve from simplicity to complexity. Gravity orchestrates a cosmic dance, drawing matter into intricate patterns. And as the universe expands, these structures evolve and interact in an endless ballet of celestial motion. The study of the universe's evolution is a journey into the unknown. Every discovery reveals new mysteries. Every observation sparks fresh questions. The grand narrative of the universe is still being written. Each new finding adds a chapter, each new theory a paragraph. The story of the universe's birth is a testament to the relentless march of progress. What seemed like fantasy in the past is reality today. Who knows what wonders the future will bring? Perhaps one day we'll witness the birth of new worlds, the emergence of new life forms, or the unraveling of the universe's ultimate fate. The universe never ceases to amaze. Its story is a reflection of our own journey of discovery. As we probe deeper into the cosmos, we come to understand not only the nature of the universe, but also our place within it. The birth of the universe is a story that resonates with the deepest human instincts. It's a story of creation, evolution, and the relentless drive towards complexity. It's a story that compels us to explore, to discover, and to understand. And as we continue to unlock the secrets of the cosmos, we bring ourselves one step closer to understanding the very essence of existence. It's easy to get lost in the sheer scale of the universe. With billions of Earth-like planets out there, it seems likely that we're not alone. But those planets exist in the same way that we do, under the same physical laws. Our entire existence depends on the precise tuning of fundamental constants such as the strength of gravity or the mass of elementary particles. This raises a question. Are we just lucky to be alive? Because the laws of nature allow for life? Or are these laws somehow tailored for us? What if the universe didn't have to be this way? Are we missing something that could change everything? This is a science show special. The fine-tuning problem is one of science's greatest puzzles. Why are the fundamental parameters of nature so finely tuned to support life as we know it? You could say that it's just chance. After all, if the universe is all there isn't anything else for the constants to be tuned to. But then again, it seems unlikely that life could arise by chance. There are just too many coincidences. Take gravity. If gravity were slightly stronger or weaker, stars wouldn't produce the right mix of elements, or planets wouldn't form in stable orbits. Or consider the strong nuclear force, which binds atomic nuclei together. If it were even slightly weaker, protons and neutrons would fly apart in most everyday objects, ending stable chemistry and ending life as we know it. Each of these examples could be multiplied many times over. So what does this mean? Are we really just fortunate to be alive in a universe that by accident happens to be suitable for life? And if not, who or what was responsible for fine-tuning the universe? One way to escape the problem altogether is to reject the notion that we live in a special universe. Maybe we're wrong to think that other universes don't exist, or maybe the laws of nature aren't the same elsewhere. This idea is known as the anthropic principle, but it does little to answer the underlying question. So let's assume that the laws of nature are universal. Where does this leave us? It means that we must turn to the origins of the universe to understand why it is this way, and not some other way. One promising approach is to trace back the evolution of the universe to its earliest moments. At first glance, it appears that we have only limited knowledge about this period. Observations of the cosmic microwave background give us insights into the universe, when it was around 400,000 years old. But before that, the universe was a hot, dense plasma, and light couldn't travel freely. That period is shrouded in mystery, and physicists call it the Dark Ages. However, within this darkness, there's potential to find clues. Scientists hope to shed light on what happened in the first millionths of a second after the Big Bang. But for that, we need to build bigger and better telescopes, both on Earth and in space. New instruments will enable us to measure the polarization of the cosmic microwave background. Polarization patterns are produced by the interaction between light and matter. They hold valuable information about the properties of that matter and the conditions in which it existed. By studying the polarization, we could learn about the plasma that dominated the early universe. How did matter clump together? How did the first stars ignite? And crucially, how did the first chemical elements form? Helium, lithium, and possibly even traces of heavier elements were forged in the hearts of long-dead stars. Capturing and analyzing these building blocks of the early universe could reveal a great deal about how matter interacted in those extreme conditions. But that's not all. The cosmic microwave background carries information about the universe. When it was around 380,000 years old, the images we currently have show a universe that's already relatively smooth, but in reality it was a much bumpier place. Tiny variations in density could help explain how matter assembled into the first stars and galaxies. While the overall structure of the early universe was quite smooth, these tiny variations could have been the seeds of cosmic structure. Galaxies form from small, overdense regions. And while we know that these structures existed in the early universe, we don't know exactly how they formed. Understanding the distribution of matter at that time could provide insight into the development of cosmic structure. This phase of the universe holds many secrets waiting to be uncovered. But unraveling these mysteries requires not only larger telescopes, but also more precise measurements and advanced data analysis techniques. It's a puzzle box with pieces scattered across the vast expanse of time. But as technology advances, we edge closer to solving it. With each new discovery, we piece together a clearer picture of the events that shaped our universe and brought life to planets like ours. Another approach to the fine-tuning problem is to question our understanding of the laws of physics. Physicists suspect that our current theories are incomplete and that there's a deeper, more fundamental theory waiting to be discovered. This idea is not just about tweaking existing theories. It's about a paradigm shift. It's about changing the way we understand the world. Think back to the late 19th century when physicists developed the theory of special relativity. Before Einstein, most physicists believed that time was absolute. Whether you were standing still or moving at a steady speed, time would be the same. But Einstein turned that around. He showed that time intertwined with space into a four-dimensional fabric, that S relative to your frame of reference. Now imagine that you and a friend are watching the same event. You're standing still relative to the Earth, so you measure time and space in a conventional way. But your friend is zooming past you in a spaceship at a significant fraction of the speed of light. For your friend, the passage of time slows down and distances in the direction of motion get squeezed. This counterintuitive idea is no longer a mystery. It's part of our everyday understanding of the universe. But once upon a time, it was revolutionary. The same kind of revolution might be on the horizon as physicists refine theories like quantum mechanics and general relativity. These two theories are the cornerstones of modern physics. Quantum mechanics explains how the universe behaves at the atomic and subatomic level, while general relativity describes how space and time intertwine on the grand scale of the cosmos. But here's the catch. They don't play nicely together. This becomes especially apparent when dealing with the universe's most extreme environments, such as black holes or the Big Bang itself. In these situations, quantum effects become significant at the very same time that gravity is strong. Fortunately, our current theories break down at that point. Physicists are working toward a new theory, a theory of quantum gravity. This theory promises to resolve the contradictions between quantum mechanics and general relativity. And in doing so, it could offer a deeper understanding of the universe. But here's the twist. Some physicists believe that this theory could also explain the fine-tuning problem. If the laws of physics are encoded in the fabric of space-time, then the very structure of space-time could hold the key to understanding why it's finely tuned for life. Imagine that the rules of nature arise from the vibrations of a cosmic string or the interaction of dimensions beyond our perception. These ideas might sound far-fetched, but they're not as crazy as they might seem. Many physicists take the idea seriously and are actively researching it. String theory, for example, is one approach that attempts to unify gravity and quantum mechanics by introducing extra spatial dimensions. These extra dimensions are thought to be curled up at extremely small scales, so we don't directly observe them. But string theorists hypothesize that they could explain the fine-tuning problem. Here's how. If the size of these curled-up dimensions is not constant but varies randomly, it could potentially explain the observed values of the fundamental constants. In other words, the seemingly arbitrary values of the constants might arise naturally from the dynamics of a more fundamental theory. But wait, there's more. Some versions of string theory predict the existence of extra dimensions, not just curled-up ones. This leads to another fascinating possibility. There might be parallel universes, each with its own set of physical laws. This concept known as the multiverse aligns with the idea of eternal inflation. Remember that? Cosmic inflation was a period of rapid expansion in the early universe. Eternal inflation suggests that this process never stopped in some regions of the universe, leading to the existence of multiple universes, each with its own physical laws and constants. It sounds like science fiction, but it's grounded in some serious mathematics. The multiverse arises naturally in certain theoretical frameworks, making it an appealing idea to many physicists. These various approaches to the fine-tuning problem highlight the remarkable creativity of theoretical physics. They push the boundaries of human imagination, exploring ideas that seem almost impossible. Yet these ideas are rooted in mathematics and physics. They're not just flights of fancy. We're just scratching the surface of understanding the universe. The fine-tuning problem is just one example. There are many other mysteries that keep scientists awake at night. Does the universe have a purpose? What happened before the Big Bang? What is the nature of dark matter and dark energy? Answering these questions will require a combination of groundbreaking theoretical work and awe-inspiring technological achievements. As we marvel at the intricacies of the cosmos, let us not forget our place in this grand scheme. We are not merely observers. We are participants in an ongoing story, the story of the universe. With each discovery, we add a chapter to this story, revealing a deeper, more profound understanding of our existence. The universe has a way of humbling us. As we explore its vastness, we realize the limits of our current knowledge. But within these limits lie the seeds of progress. Every unanswered question, every unsolved mystery is a challenge, a beacon guiding us toward new discoveries. So let us embrace the unknown, for in the words of Carl Sagan, the most exciting thing about science is that it never stops being new. Have you ever looked up at the night sky and wondered what it all means? What is this vast universe, and how did it begin? The answer, the Big Bang, challenges our understanding of time, space, and the very nature of reality. Join us on a journey through the origins of our cosmos, uncovering the mysteries that surround the Big Bang and what it means for us here on Earth. The Big Bang Theory. A universe in a nutshell, the Big Bang Theory is more than just an explosion. It's the cornerstone of modern cosmology, explaining how the universe evolved from a hot, dense state billions of years ago to the vast cosmos we observe today. But what came before the Big Bang? What was it like in the first moments of creation? The idea that the universe began with a bang emerged in the early 20th century, uniting scientists like Georges Lemaitre, Alexander Friedman, and Albert Einstein in its pursuit. They proposed that the universe had a starting point, a singularity where space, time, and matter were infinitely dense and hot. As the universe expanded, it rapidly cooled, allowing particles to form and interact. Over billions of years, gravity pulled these particles together, forming stars, galaxies, and planets. The birth of space and time, a quantum leap. One of the most mind-boggling aspects of the Big Bang is the notion that time and space began at the same moment. Before the Big Bang, the concepts of time and space didn't apply. There was no before because time hadn't started yet. Space wasn't empty because it didn't exist. The universe went from nothing to something in a quantum leap that defies our everyday experience and the laws of physics we observe. Scientists have attempted to understand this moment through theories like quantum cosmology, which incorporates principles of quantum mechanics to explain the universe's beginnings. However, the exact mechanism that triggered the Big Bang remains unknown. It's a mystery that continues to elude even the most brilliant minds in cosmology. The cosmic microwave background radiation, a fading echo. A key piece of evidence supporting the Big Bang theory is the cosmic microwave background radiation. This faint glow permeates the universe and was likely emitted when the universe was just 400,000 years old. At this point, the universe had cooled enough for protons and electrons to combine, forming neutral hydrogen atoms. This allowed light to travel freely, offering a snapshot of the universe as it was in its infancy. By analyzing the cosmic microwave background, scientists have mapped the distribution of matter in the early universe and studied its evolution over time. It's like having a window into the past, observing the universe in its earliest stages. The abundance of light elements, a recipe for creation. The Big Bang Theory also explains the abundance of light elements like hydrogen, helium, and lithium in the universe. These elements were produced in the first minutes after the Big Bang, when the universe was unimaginably hot and dense. Nuclear fusion reactions created these elements from the fundamental particles that existed after the initial explosion. The observed abundance of these elements matches predictions made by the theory, providing strong evidence for its validity. The expanding universe, a never-ending journey. One of the most fascinating aspects of the Big Bang Theory is the idea of an expanding universe. In 1929, Edwin Hubble discovered that galaxies were moving away from us, indicating that the universe was expanding. This observation led to the theory that the universe began as a single point and has been expanding ever since. Today, scientists use distant supernovae as standard candles to measure the rate of cosmic expansion, revealing a universe that is accelerating in its growth. This acceleration is driven by a mysterious force known as dark energy, which makes up nearly 3/4 of the universe. While dark energy remains elusive, its presence supports the idea that the Big Bang was not an isolated event, but a moment in an ongoing process of cosmic evolution. What the Big Bang means for us? More than just a beginning? The implications of the Big Bang extend far beyond the realm of scientific inquiry. They challenge our understanding of time, space, and our place in the grand scheme of existence. Let us explore some of the ways the Big Bang Theory impacts our understanding of the universe and our lives. Stardust origins, the Big Bang's connection to life. One of the most profound links between the Big Bang and human existence lies in chemistry. In the first minutes after the Big Bang, the universe forged the simplest elements: hydrogen, helium, and traces of lithium. These primordial elements made up the raw material of stars. Inside those stars, nuclear fusion created heavier elements: carbon, oxygen, nitrogen, iron, the very ingredients of life. When massive stars exploded in supernova, they scattered those elements into space, seeding future generations of stars, planets, and eventually us. This means that the calcium in our bones, the iron in our blood, and the oxygen we breathe all originated from processes set in motion by the Big Bang. Without the cosmic expansion and cooling that followed, stars could never have formed, and life as we know it would be impossible. The phrase "we are stardust" is not poetic metaphor. It is literal fact. The cosmic timeline and Earth's place. By studying the Big Bang and the evolution of the universe, scientists have built a cosmic timeline that places Earth and humanity in a much larger story. The universe is about 13.8 billion years old. Earth formed only about 4.5 billion years ago, and humans appeared a mere 300,000 years ago. On this scale, we are newcomers, arriving at the last possible moment in a long cosmic drama. This perspective reshapes our sense of identity. It reminds us that Earth is not the center of the universe, but one small world in a vast, evolving cosmos. It also deepens our appreciation of the delicate balance of conditions that allowed life to arise here, a balance shaped by billions of years of cosmic evolution. Technology born from cosmic curiosity. Understanding the Big Bang hasn't just advanced our philosophical understanding of the universe. It has also driven practical advances in technology. The search to detect and study the cosmic microwave background led to the development of extremely sensitive detectors. The same technology is now used in medical imaging, wireless communications, and even airport security scanners. The data analysis techniques developed for large sky surveys and cosmological simulations have fueled breakthroughs in computing, artificial intelligence, and big data science. Even GPS satellites, which guide our cars and phones, rely on corrections from Einstein's general relativity, the same framework used to describe cosmic expansion. Without these corrections, GPS would drift by kilometers each day. In other words, our modern world literally depends on the physics born out of understanding the universe. A shift in worldview. The Big Bang also shapes how humanity understands its place in the cosmos. Ancient civilizations once believed the universe was eternal and unchanging, with Earth at the center. The discovery of cosmic expansion overturned that view, showing us a dynamic universe with a definite origin. This realization has profound philosophical consequences. It suggests the universe had a beginning, a moment when time, space, and matter all came into existence. That challenges us to think differently about existence itself, about creation, about why there is something rather than nothing. Some find spiritual resonance in this story, while others see it as a triumph of human reason and scientific inquiry. Either way, the Big Bang bridges science and philosophy, grounding human questions about origins in the language of physics and evidence. The search for life beyond Earth. Cosmology also fuels one of humanity's most exciting pursuits. The search for extraterrestrial life. The Big Bang established the physical laws and elemental abundances that made stars and planets possible. By studying cosmic evolution, astronomers can estimate how many potentially habitable worlds exist. Recent discoveries of exoplanets suggest that planets are common, and many lie in habitable zones where liquid water could exist. If life is widespread, then its roots, like ours, trace back to the Big Bang. Every alien organism, if it exists, would be made of the same atoms forged in the furnaces of stars, from the same hydrogen born in the universe's first minutes. Understanding the cosmic origin story therefore unites all potential life, human or alien, in a shared ancestry with the universe itself. The fragility of our moment. Finally, studying the Big Bang highlights the fragility of Earth's place in cosmic history. The conditions that gave rise to us are rare and precious. The expansion of the universe, the synthesis of elements, the formation of stars and planets, all had to align for life to emerge here. This awareness carries a responsibility. By seeing ourselves as children of the cosmos, we gain perspective on the need to protect our fragile world, not as an isolated planet, but as part of a larger, ongoing cosmic story. Why it matters. The Big Bang is not distant history. It is the foundation of everything we see, touch, and are. It explains the atoms in our bodies, the stars in the night sky, the tools we use every day, and the very possibility of life itself. To study the Big Bang is to study ourselves, our origins, our place in time, and our shared future in a universe that is still evolving. As we continue to probe the mysteries of the cosmos, the Big Bang theory serves as our guiding light, illuminating the path to understanding our existence and our place in the grand tapestry of the universe. The story of the Big Bang is not just a scientific narrative, it's a story about us. It's a story about where we came from and the incredible forces that shaped our existence. As we look up at the stars and ponder the vastness of space and time, we are reminded of our small but significant place in the grand scheme of things. The Big Bang theory has revolutionized our understanding of the universe and our place within it. It's a testament to the power of human curiosity and the relentless pursuit of knowledge. And as we continue to explore the mysteries of the cosmos, the Big Bang serves as our North Star, guiding us towards a deeper understanding of our existence and the amazing universe we call home. We hope you enjoyed this journey through the Big Bang and its profound implications. In the latest video, we told you the story of the heat death of the universe, where everything is cold and dark and dead. We know that's not where the story started. The universe began with the Big Bang, and while that may seem obvious for a long time, it wasn't. There were plenty of ideas about the nature of the universe back before the early 20th century, but none of them really had any evidence to back them up. And so today, we're going to tell you the story of the Big Bang, how over several decades astronomers and physicists gradually pieced together the events leading up to the birth of the cosmos. We'll tell you about the discovery of the cosmic microwave background radiation, the confirmation of the Big Bang, and how we used satellites and supercomputers to test the accuracy of the Big Bang theory. But before we dive into the story of the Big Bang, we'll start our story in the early part of the 20th century. Up until that point, it was generally assumed that the universe was static. It always existed and always would. That idea seemed pretty sensible, because why would the universe have a beginning or an end if it's infinite?
Wow.
Well, it turns out that there's actually nothing in physics that says the universe has to be eternal. You see, Einstein was trying to develop a theory that described how gravity worked. He developed a set of equations that could describe how space and time warped in response to matter and energy. They're now known as Einstein's general theory of relativity. Now, While these equations are fantastically complex, they can be solved in certain cases. One such case is when there's no matter or energy present at all. Einstein realized that in this hypothetical scenario, space and time would be entirely empty, which kind of goes against what we observe in the real world, where there are always things somewhere. So to make his equations match up with reality, he added a fudge factor to his equations, a mathematical trick that cancels out the effects of gravity and keeps the universe still. This is why Einstein famously said, "God doesn't play dice." He felt that the addition of the constant broke the probabilistic nature of quantum mechanics, since the constant ensured that the universe would be unchanging. However, that didn't sit well with everyone. In 1917, a Russian mathematician called Alexander Friedmann pointed out that Einstein's equations could, in fact, describe a universe that expanded over time. Friedmann didn't pursue this idea very far, though. He had no idea of how the universe might have evolved over time. But Einstein didn't need to read any further than the title of Friedmann's paper, which was on the curvature of space. The title alone was enough for Einstein to write, "This is infinitely bad." Another scientist who wasn't satisfied with the idea of a static universe was Georges Lemaître. Also in 1922, he put forward his own hypothesis for how the universe might work, which included expansion. Unlike Friedmann, Lemaître took his idea further, suggesting that the universe began from a single point and then expanded outwards. He named his hypothesized starting point the primeval atom. He published his idea in French, which is probably just as well, because if he'd published it in English, it would have been hard to say primeval atom without laughing. But the idea wasn't taken seriously by anyone. Part of this was because Lemaître was a Roman Catholic priest, and at the time, scientists struggled to take anything a clergyman said about the universe seriously. Additionally, while mathematicians had come up with equations that seemed to support an expanding universe, they had no idea how to test whether those solutions were correct. For that, they needed someone who could actually observe the universe. Enter Edwin Hubble. In 1929, while observing a nebula in Andromeda, Hubble noticed something strange. All of the lines in the spectrum of light coming from the nebula were shifted to longer wavelengths. It was redshifted. Since the 1920s, scientists had understood that objects moving away from us would exhibit this type of redshifting. If you look at the spectrum of light from a star in our galaxy that's moving away from us, the star's spectral lines will be redshifted. But this isn't usually something you see with galaxies. And at first, Hubble didn't realize that that's what was happening here. He assumed that the redshift was due to some intrinsic property of the galaxy itself. Hubble then looked at a number of other galaxies and found that they, too, were redshifted. However, there was one key difference between the light from Andromeda and the light from the others. The light from Andromeda was only slightly redshifted, whereas the light from the others was strongly redshifted. This meant that the more distant the galaxy, the faster it was moving away from us, and that was unprecedented. Nothing in the universe was known to move faster than the speed of light. But if Hubble's observations were right, then something was speeding up as the universe got bigger. Hubble then graphed the distance to each galaxy against its velocity. Now, the graph wasn't a flat line as would be expected if the universe was static. It was a straight line passing through the origin with a positive slope. And that gave scientists the missing piece of the puzzle. They could test Lemaître's hypothesis. If the universe was truly expanding, then every galaxy would be moving away from every other galaxy. But that shouldn't happen if the universe was static. It was like a key fitting into a lock. Everything finally slotted into place. So the next question was, how could they prove it? That proof came around 30 years later with the discovery of the cosmic microwave background radiation. But before we get to the discovery, if you're enjoying this video, stay tuned for more stories of scientific discoveries. By the late 1960s, Penzias and Wilson were working as engineers at Bell Telephone Laboratories. One evening, they went to check on an unusual noise they'd heard coming from their equipment. At first, they thought it might be pigeon droppings, hence the presence of a bird-dropping joke in the title. But it wasn't. After investigating, they realized that the noise was coming from everywhere in the sky. Because the universe is expanding, the waves of microwave radiation were stretched, causing them to fall within the microwave band of the electromagnetic spectrum. It was the perfect match for Lemaître's theory. This discovery earned them the 1978 Nobel Prize in Physics. In hindsight, the discovery of the cosmic microwave background radiation seems almost inevitable. Like the discovery of Neptune had seemed almost inevitable after the irregularities in Uranus' orbit had been noted. But at the time, it was pure luck. The pair hadn't even been searching for it. In the following decades, scientists sent satellites into orbit to map out the details of the CMB. The COBE mission in 1989 produced a full sky map showing that the CMB was uniform. It also found tiny variations in temperature across the sky that revealed where matter was condensing to form stars and galaxies. The WMAP mission in 2001 and the Planck satellite in 2009 created even more accurate maps. Today, we have a detailed map of the entire sky in microwave radiation. We know that the universe is expanding, and we know that it began from a hot, dense state. But exactly how did the universe evolve from that state? Scientists turned to simulations. They began feeding information about the universe into computers to try to recreate the evolution of the cosmos. Today, computer simulations allow astronomers to track the path of individual photons as they interact with matter to form stars and galaxies. They can then compare those simulations with what we observe in the real universe to see how well the models fit with reality. To date, those comparisons have shown that the Big Bang model fits the data well, but it doesn't fit it perfectly. One example of this is the lack of small-scale structure in the CMB. Our computer models predict that there should be more small-scale structure in the CMB than we actually observe. It could be that the model is wrong and the universe didn't begin with the Big Bang. But it could also be that the model is right and we read just missing something in our description of physics. It's a similar story with the large-scale structure of the universe. The distribution of galaxies in the universe appears to contradict our models. But again, it could be that our model is missing something. Today, scientists are still working to perfect the Big Bang theory. It's no longer a theory in the sense that it means it's a hunch or a guess. It's a theory in the scientific sense, meaning that it's backed up by masses of evidence. However, there are still unknowns. We don't know what dark matter is, nor do we know what dark energy is. We also don't know what triggered the Big Bang in the first place. Then there are anomalies like the lack of small-scale structure in the CMB and the apparent contradiction in the large-scale structure of the universe. Those are all problems for scientists to solve. Maybe one day they'll find that the Big Bang wasn't quite right. Maybe they'll discover that the universe didn't begin in a hot, dense state. But regardless of what they discover, it'll be another incredible chapter in the story of our existence. The Big Bang Theory has given us a framework to understand the birth and growth of our universe. It's allowed us to look out at the cosmos and see its history written across the sky. But every answer brings new questions. As we look to the future, the story of the Big Bang becomes not just about the past, but about the destiny of the cosmos and our place within it. What came before the bang? Perhaps the deepest question is one that the Big Bang Theory itself cannot answer. What happened before the beginning? When we use the Big Bang Theory to try and rewind time, we hit a wall. There are mathematical solutions to Einstein's equations that describe a universe with no beginning, and physicists are actively looking for evidence of what might come before. The problem is that such evidence would be difficult to detect because the Big Bang tells us that all the information that existed in the early universe was destroyed in the first few milliseconds. So any evidence of what came before would likely be gone forever. However, other theories propose that our universe was born from something larger. One such idea is that the Big Bang was a quantum fluctuation, a brief but intense burst of activity in an otherwise empty space. Supporters of this idea say that the quantum vacuum isn't really empty, but filled with virtual particles that pop in and out of existence. Our universe may have started as one of these virtual fluctuations and then expanded exponentially, carrying the germ of everything we know today within it. Other theories suggest that our universe was born from the collapse of a previous universe. A big crunch where space compressed to an infinitely dense point, breaking the known laws of physics. These ideas are speculative, but they hint at the tantalizing possibility that our Big Bang wasn't the first, but just the latest in an endless cycle of creation and destruction. Still others propose the multiverse, a vast and complex structure containing multiple universes. In this scenario, our Big Bang was just one spark among countless others, each with its own physical laws and history. If true, that means life, Earth, and humanity could be extremely rare, or maybe very common. Either way, our view of the universe has changed drastically since the days when the Earth was thought to be the center of all creation. The Big Bang shows us that our solar system and planet are just one small piece of a much bigger picture that is constantly changing and evolving. Unlocking the secrets of the universe's beginning may help us understand not only where we came from, but also where we're going. Dark matter and dark energy. The hidden majority. We know less about the building blocks of the universe than you might think. Yes, we can observe the stars and planets and galaxies scattered throughout the cosmos. But most of the universe is invisible. Dark matter, 5 times more abundant than ordinary matter, holds galaxies together with its unseen gravity. And dark energy, even more mysterious, drives the accelerating expansion of space. Together, these two make up over 95% of the universe, yet their true nature remains elusive. Astronomers are working hard to unlock the secrets of dark matter and dark energy, and they have some promising leads. Several experiments are underway to detect the hypothetical particles that make up dark matter, while others are measuring the properties of dark energy in hopes of pinning it down. Some scientists even believe that dark matter and dark energy could be related, that they might be different manifestations of the same underlying phenomenon. If that's true, it could revolutionize our understanding of the universe. Not only would it solve 2 of cosmology's biggest mysteries, but it could also point the way to new technologies and new sources of energy. But even if the two turn out to be unrelated, understanding them better will give us a deeper appreciation of the universe and our place within it. After all, the fact that so much of the universe is invisible doesn't mean it's unimportant. In fact, dark matter and dark energy may be the key to unlocking some of the deepest mysteries of existence. So, as astronomers continue to probe the depths of space, they're also delving into the hidden majority, seeking to bring the invisible into the light. The fate of the universe, when we think about the Big Bang, we're often focused on the beginning. But it's important to remember that the story doesn't end there. The Big Bang also tells us something about the fate of the universe. According to the theory, the universe began as a hot, dense ball of energy and matter that expanded and cooled over time, eventually forming the stars and galaxies we see today. But the story doesn't have to end there. As astrophysicists study the evolution of the universe, they're also thinking about its ultimate fate. One possibility is that the expansion of the universe will continue to accelerate, carrying galaxies away from one another until the heat death of the universe, when all stars go out and only cold darkness remains. Another possibility is that the expansion will flip and our universe will literally begin to collapse, ending in a fiery death known as the heat death. Some scientists even believe that the universe could expand and contract in a repeating cycle, an eternal oscillation between creation and destruction. Understanding the ultimate fate of the universe is not just a matter of scientific curiosity. It could have profound implications for life on Earth. If the universe is heading towards a heat death, for example, it could mean that life as we know it has only a finite amount of time to explore the cosmos. On the other hand, if the universe is headed towards a big rip, it could mean that humanity has the opportunity to build a spacefaring civilization that can survive the end of our solar system and even the end of the universe itself. Of course, these are just possibilities. The ultimate fate of the universe is still unknown. But as astrophysicists continue to study the evolution of the cosmos, they'll get closer and closer to the truth. And who knows what other mysteries they'll uncover along the way. Humanity's role in the cosmic story in the past, many cultures had their own creation stories, often centered around gods or mythical beings. But the Big Bang Theory offers a different perspective. It suggests that the universe we live in today formed from a hot, dense state billions of years ago through a series of natural processes. This idea challenges traditional views of humanity's place in the cosmos, suggesting that we are not the center of a divine plan, but rather the product of a vast, impersonal physical process. However, the Big Bang Theory also offers a sense of wonder and awe. The idea that all the matter in our bodies, the atoms that make up the air we breathe, and the stars that twinkle in the night sky, were forged in the intense heat of a primeval explosion is both humbling and inspiring. It suggests that we are made of the same stuff as the universe itself, and that our very existence is a testament to the power of natural laws. But perhaps the most important lesson we can learn from the Big Bang is that our planet and our solar system are just a small part of a much larger whole. The universe is vast and ever-expanding, containing countless galaxies and stars, and we have only begun to explore it. This realization should inspire us to be curious, to ask questions, and to push the boundaries of our knowledge. As we learn more about the universe, we learn more about ourselves, the tools of tomorrow. The Big Bang Theory is a remarkable scientific achievement, but it's not the end of the story. In fact, it's just the beginning. To further our understanding of the universe, we need to develop new tools and technologies to explore the cosmos in greater detail. Fortunately, this is already underway. Astronomers are developing next-generation telescopes that will peer deeper into space and time than ever before. They're also building new observatories on the ground to detect gravitational waves, ripples in space-time that can reveal the secrets of the most violent events in the universe. Experiments to detect dark matter and dark energy are also underway, as well as efforts to measure the properties of antimatter, which could provide clues about the nature of the universe itself. But it's not just new tools we need. We also need new ideas. Physicists are working to develop a theory of everything that can explain the fundamental forces of nature. Meanwhile, cosmologists are searching for new models of the universe that can account for all the strange phenomena we observe today. These efforts are not without their challenges. Many of the experiments and observations required to test new ideas are incredibly difficult and expensive, but the potential rewards are enormous. By pushing the boundaries of our knowledge, we can not only learn more about the universe, but also about ourselves and our place within it. Final questions. The Big Bang Theory has revolutionized our understanding of the universe, but it's not the final word. There are still many unanswered questions about the nature of reality, the origin of life, and the ultimate fate of the cosmos. Some of these questions may never be answered, but that shouldn't stop us from asking them. By pondering the deepest mysteries of existence, we can expand our minds and push the boundaries of human knowledge. Who knows what wonders we might uncover in the process? The universe began in fire, expanded into light, and continues into mystery. From the first spark of creation to the galaxies above us tonight, the story of the Big Bang is the story of everything, and it is still being written. In that story, one thing is certain: humanity, with our curiosity and courage, is destined to keep searching for the truth of how it all began. Big Bang Theory, the prevailing cosmological model for the universe, describes the universe's evolution from an extremely hot, dense state billions of years ago to its present state, expanding and filled with galaxies, stars, and planets. The Big Bang Theory states that the universe began as a singularity, an infinitely dense and hot point, and then expanded rapidly, cooling as it did so. This expansion continues today, and the theory provides a framework for understanding the evolution of the universe over time. Evidence supporting the Big Bang includes the redshift of distant galaxies, the abundance of light elements, and the cosmic microwave background radiation. The theory also makes predictions about the future of the universe, such as its eventual heat death, or the heat death of the universe. This is a theoretical concept that describes a future state of the universe where all stars have burned out, leaving only cold, dark matter. Despite its success, the Big Bang Theory has limitations and cannot explain certain phenomena such as dark matter and dark energy. Additionally, it leaves some questions unanswered, such as what happened before the Big Bang, or what caused the rapid expansion of the universe in the first few seconds after its formation. The Big Bang Theory remains the most widely accepted explanation for the origin and evolution of the universe, and it continues to be refined and expanded upon as our understanding of the cosmos grows. What do you think? Please leave your thoughts below. And if you enjoyed this video, please like and subscribe. Thanks for watching.